what is known as a single tuned filter. So, please note we are trying to see what is happening on the AC side. So, we have seen that there are current harmonics. So, the idea is the harmonics on the AC side will not flow into the AC system, it will actually flow into the filter. Though see, we can't actually eliminate the current harmonics in the converter. There are current harmonics in the converter that can't be eliminated, or that can't be even minimized. What one can do is try to minimize the currents in the AC system. So, that means where will the current harmonics flow? If it has to flow in the converter, it has to flow somewhere on the AC side. So, that is the path is provided by the filter. Okay, that is the idea. So, that it does not flow in the. So, what I am trying to say is, okay, let me try to say here. Suppose I have an AC network. So, I have a converter here. So, I provide a path here. Okay, let me elaborate this. So, there are harmonics in the currents on the AC side of the converter. So, if nothing is done, it will flow in the AC network also. So, if I provide a path in the form of a filter, okay, so the currents will actually be supplied, I mean, it's actually currents will flow through the filter. So, it will not flow through the network, that is the idea. Okay. So, we will look at more details how this can be done. So, let me take straight away an example, a single tuned filter. So, I mean, have you heard of single tuned filter? By any chance heard of this name single tuned filter, or at least guess what can be a single tuned filter? Yeah, it is actually designed to allow current at one particular frequency, I mean essentially a harmonic frequency. Okay. So, what does it contain? L and C. Okay. So, it should have an inductance, inductor and a capacitor. So, let me draw the circuit. The circuit is like this. It has a capacitor in series with an inductor, in series with a resistance. Okay. So, we will see why we need all this. So, there is a capacitor with capacitance C, there is an inductor with inductance L, and there is an effective resistance in the circuit, which is R. Okay. So, this is a single tuned filter. Now, if I want to say eliminate one particular frequency, which frequency should I consider to be most critical? Huh? Yeah, which one? I am talking about AC filter, to filter out the current harmonics. 11th. Suppose I want to design a filter for 11th harmonics, then I have to choose the value of L and C, so that this becomes a resonant circuit for the 11th harmonic. Okay. Now, can I exactly design the value of L and C so that it is tuned for the frequency of the harmonic that it is supposed to eliminate, or at least supposed to suppress? Why?
Impedance is omega L, that of impedance is minus j omega c.
Okay.
So, we will design L and C such that these two cancel out.
No, can I always design a single tuned filter, that means essentially select the values of L and C such that the resonant frequency is equal to say 11th order harmonic frequency? Yeah, theoretically yes, but in practice what can be the problems? See, when I say I have a 50 hertz system, the 11th order harmonic is 550 hertz, but frequency is not exactly 50. Frequency keeps changing. We know nominal frequency is 50. So, frequency will vary over a band. So, frequency is not exactly 50, means it varies over a small band, the 11th order will vary over a larger band. Okay. So, the harmonic frequency is not a fixed number, it is a quantity which is within a certain band. That is one thing. Then what about the value of L and C? Though I select L and C, no manufacturer will give an inductor and say the L will remain constant forever at this value. The manufacturer will say L is this value plus or minus by some amount. Okay. Even the capacitance will be this value plus or minus some amount. So, L and C are also some numbers which vary over a certain band. Okay. So, we can't say that L will remain constant at this band. Now, actually when it comes to capacitance, the capacitance is more a variable. I mean the band within which the capacitance value changes is much larger or much more significant compared to the band over which the inductance changes. Now, that is because it is more because of aging, I mean as time passes, and also the change in temperature. Capacitance is dependent on temperature. Now, the temperature can be due to two reasons: the ambient temperature itself, which has nothing to do with what is going on in the capacitor, or due to the heat produced in the capacitor itself. Okay. So, that also decides the temperature. So, temperature will have an effect on the capacitance. So, essentially C and L are not constants and the frequency itself is not constant. Of course, R is not affecting any of these things. See, R is just resistance which is coming there. We will see why we have R here, that we will see later. But the variations of L and C will have problems, and the frequency itself is not a constant. Okay. So, in practice a filter is not always tuned exactly to the frequency of the harmonic that it is intended to suppress. So, there are so many reasons. One is there can be the reasons are: number one, the power system frequency may change. Power system frequency, and hence, say I gave an example of just a 11th harmonic. We can also design a single tune filter for 13th harmonic. Then the 13th order harmonic frequency is 13 into 50 hertz. Okay, and the band will appropriately increase. So, the band in which the harmonic frequency stays is getting larger and larger as the fundamental frequency, as you increase the frequency order because of the fundamental frequency itself not being a constant. Okay. So, power system frequency and hence the harmonic frequency may change. Then inductance of the inductor may change. Inductance of inductor may change. Capacitance of capacitor may change. In fact, as I said, the capacitance change is more significant than inductance change. So, change in capacitance is more significant than the change in inductance. So, this is actually because of aging, and because of aging means as you keep on using capacitor for more and more time, as years pass by, it ages. Okay. So, the capacitance itself will change, and change in temperature. So, change in temperature itself can be either due to ambient temperature or self heating. So, that is why the capacitance change is more significant than inductor change, but compared with inductance change or capacitance change, the frequency change is in fact more significant. Okay. So, the system frequency changes are more significant compared to the inductance change or capacitance change. So, the system frequency will have a more effect that will result in the filter not being tuned to the frequency at for which it is intended to work. Okay. So, what we will try to do is we will try to quantify this deviation in this behavior of the filter not being exactly tuned. Okay. So, we will somehow try to quantify this. So, for that we will define a quantity. So, define a quantity called delta. This is defined as omega h minus omega h o divided by omega h o. Now, let me say what is this omega h, where omega h is the actual harmonic frequency, which can be written as, okay, let me first say what is omega h, the actual harmonic frequency. So, from the notation you should be able to make out that it is not frequency in hertz, it is angular frequency. Please note it is angular frequency. Okay. Now, I will write omega h as omega h star plus delta omega h, where omega h star is the nominal harmonic frequency. That means, if I want to design the filter for 11th harmonic in a 50 hertz system, 50 hertz is the nominal value. So, the nominal value of 11th harmonic is 550 hertz. Okay. So, where omega h star is the nominal harmonic frequency. Then omega h o is there in the definition of delta. Omega h o by definition is 1 by square root of L C. Now, are you familiar with this formula? I do not know, you might have come across filter earlier in some course. So, if I want to design the filter for the frequency omega h o, which is the angular frequency, then L and C should satisfy this equation. Omega h o is 1 by root L C. You are familiar with that, right? Okay. Now, as I said, L and C themselves are not constants. So, I write this expression for L as, so L itself is not a constant, I will say L is equal to a nominal value L star plus delta L, and C is equal to C star plus delta C. Now, please note this omega h star, L star, C star are all constants, they are some fixed values. The deviation is in the form of delta omega h for frequency, delta L for inductance, and delta C for capacitance. Now, this L star, C star and omega star are actually related. So, can I say when everything is ideal, omega H star is the nominal value, it is a fixed value. So, can I establish a relationship between omega H star, L star, C star? So, this is exactly equal to 1 by under root L star C star. Now, please note omega HO is not a constant. Omega HO is not a constant because L is not a constant, C is not a constant in general, whereas omega H star is a constant. Now, if you look at the definition of delta, omega H is not a constant, omega HO is also not a constant. So, one should not assume that I am trying to take the difference between a variable quantity and a fixed quantity. Both are variable quantities. Okay. So, we say that this delta is a quantification of the behavior of the filter in not being tuned to the frequency for which it is intended to work. Okay. Now, what I mean, this definition by itself may not be of much use. We will try to write it in a slightly different form. Okay. So, I will write this definition delta as omega H by omega HO minus 1, which can be written as, I will substitute the expression for omega HO. So, just now we defined omega HO. Omega HO is 1 by root LC. So, I can write this as omega H under root LC minus 1. Okay. Now, the next thing I am going to do is, I will try to expand this right hand side in the expression for delta by using a Taylor series, and the Taylor series is about the ideal values omega H star, L star, C star. Now, please note delta is dependent on omega H, is dependent on L, it is dependent on C, and all these three quantities have an ideal value omega H star, L star, C star. Okay. So, it is a function of three quantities. So, let me try to expand this using Taylor series, but at the same time I will not write all the infinite number of terms. So, I will restrict it to few terms. Okay. So, when I do a restriction to few terms, then it becomes only approximate. So, what is the first term? So, yeah, I am trying to do a Taylor series expansion about the ideal values omega H star, L star, C star. So, the first term will be nothing but the right hand side itself with omega H replaced by omega H star, L replaced by L star, C replaced by C star. So, omega H star under root L star C star minus 1, that is the first term. Then what sort of terms come next?
Partial differentiation.
Yeah, partial derivatives with respect to omega H, with respect to L, with respect to C. Okay. So, then I need a partial derivative with respect to omega H of omega H under root LC minus 1, and this partial derivative is evaluated at omega H equal to omega H star, L is equal to L star, C is equal to C star into what? Yeah, delta omega H is nothing but omega H minus omega H star. So, so when I say delta omega H, it actually means omega H minus omega H star. Okay. So, that is the partial derivative with respect to omega H. Similarly, we have partial derivatives with respect to L and C. So, the next term is dou by dou L of omega H under root LC minus 1 evaluated at omega H equal to omega H star, L is equal to L star and C is equal to C star into delta L. Again, delta L is L minus L star plus dou by dou c of omega h under root LC minus 1 evaluated at omega h equal to omega h star, L equal to L star, C equal to C star into delta C. So, then subsequently we will have the second order partial derivatives and so on. Now, I will restrict myself to first order partial derivatives. That is why I have replaced the equality sign by approximately equal to. Okay. So, let us see how to get this partial derivatives. So, this is equal to, what is the sum of first two terms? Omega h star L star C under root L star C star minus 1. 0, it is 0. See, just now we saw that omega h star is 1 by under root L star C star. So, the first two terms in the expression for delta now will be 0. Okay. Now, if I take the partial derivative, that is the second, the first partial derivative is with respect to omega h. So, this is equal to, so the partial derivative of omega h under root L c minus 1 is nothing but under root L c with the L replaced by L star and C taking a value of C star into delta omega h. Now, please note I have not explicitly stated here where delta omega h is omega minus omega h star, delta L is L minus L star, delta C is C minus C star. Okay. So, this is the first partial derivative. Then the partial derivative with respect to L. So, when I take partial derivative with respect to L, the other quantities are assumed to be constants. So, the other quantities are omega h and root c, okay, omega h and root c, and it is not just taking the partial derivative and evaluating that partial derivative at omega h equal to omega star and c equal to c star. Then the partial derivative of square root of L is 1 by 2 root L, that is evaluated at L star into L minus L star delta L. Plus the partial derivative again with respect to C. So, omega h star, so omega h root L will take a constant value, that is omega h star L star. So, the partial derivative with respect to C has to be taken for root C. So, it is 1 by 2 root C and it is evaluated at C star into delta C. This is okay. Now, let us try to simplify this. So, I will write the first term as delta omega h square root of L star C star can be written as omega h star in the denominator. Okay. So, square root of L star C star is 1 by omega h star. Okay. Then, what is the simplification of the second term? Delta L by 2 L star, delta L by 2 L star. So, that is because omega h star is 1 by root L star C star. Okay. So, similarly, the third term is delta C by 2 C star. So, what we have got here is the expression for delta. Of course, it is an approximate, but for all practical purposes, it is the expression for delta that we defined. Now, as I said, the variation of C, that is delta C, is more significant when compared with delta L, but when compared with delta omega H, the variation of delta L and delta C are actually much smaller. Okay. So, the effect of system frequency change will have a significant effect on this delta. So, what we will try to do is we will try to design a filter, in fact a single tune filter for a particular harmonic frequency. So, we will try to do a very simplified design. We will make some assumptions. So, this is a general expression for delta, but for the sake of simplifying the design, we will assume that the changes delta L and delta C are negligible. Okay. So, let us do a simplified design where I will assume that delta L is equal to 0 and delta C is also equal to 0. Now, please note what I have got is the general expression for delta. I am just taking a simplified case for the sake of studying design, which will be much more simplified. Okay. So, we will see that this I mean, in spite of this, it will be much, I mean, it is not so easy, design is not so easy, it is a very complicated stuff. Then delta can be written as delta omega H by omega H star. Now, if delta L is 0 and delta C is 0, can I relate omega HO and omega H star? Look at the definition of omega HO, look at the definition of omega H star, look at the definition of delta L, delta C, and suppose delta L is 0, delta C is 0. Huh? Sorry? Same? Same. Okay. So, omega HO is equal to omega H star. Okay. Please note this, we get only if delta L is 0, delta C is 0, otherwise no, otherwise no. Okay. Now, if I take omega H, the actual harmonic frequency, then can I okay. Now, one point to note is that when I say, okay, let me write one more step. If I take delta omega H is by definition omega H minus omega H star divided by omega H star. So, that's by using the definition of delta omega H. Now, just now I said omega H star and omega HO are one and the same. So, I mean, instead of omega H star, I could have used omega HO. So, from this I can write omega H as omega H star into 1 plus delta. Okay. So, we have this filter. See, filter is very simple. It has an R, it has an L, it has a C, all are in series. R, L, C are in series. Now, let us take this single tune filter and try to write an expression for the admittance of the filter at a particular frequency, which is the harmonic frequency. So, admittance of the filter at the harmonic frequency. Now, please note admittance and impedance are dependent on frequency. So, if I take admittance of the filter YF, and since I am evaluating it at the harmonic frequency, I add one more subscript H, and this is a complex number. So, I just use arrow to indicate that it is complex. Okay. So, this can be written as conductance plus J times susceptance. Okay. So, I will not again use the subscript H, it is understood. Okay. So, GF plus JBF. GF and BF are real numbers. So, if I take 1 by Y of H, I get the impedance, So, what is the impedance? Now, impedance I can write. Say, please note GF and BF were not there in the parameters or in the figure of the single tune filter, but I had said R, L and C. So, admittance, if I mean the reciprocal of admittance is impedance, which is equal to R plus J times the effective reactance. So, what is the effective reactance? Yeah. So, omega H L minus 1 by omega H C. So, this can be written as R plus J. Omega H is, just now I got an expression for omega H. It is omega H star into 1 plus delta into L minus 1 by omega H star into 1 plus delta into C. So, this can be written as R plus J times, so omega H star squared 1 plus delta square L C minus 1 divided by omega H star 1 plus delta C. Is this okay? Now, is there any simplification possible? Yes, any simplification possible? LC is equal to? Yeah, please note delta L is 0, delta C is 0. So, if delta L is 0 and delta C is 0, by definition of delta L, it means L is equal to L star, C is equal to C star. That is what we mean by delta L 0, delta C 0. So, if L is equal to L star and C is equal to C star, omega H star is 1 by root L star C star. So, this gets simplified to R plus J 1 plus delta whole square minus 1 divided by omega H star 1 plus delta C. Okay. So, this can be written as R plus J. So, if I expand 1 plus delta whole square, I get delta into 2 plus delta divided by omega H star. So, I will do one more manipulation here. So, I will write this omega H star into C as what? Okay. Suppose I take 1 plus delta here. Can I write omega H star into C as? Yeah, under root of C by L. So, can I write this as root L by C? Now, what is this delta? Delta is some deviation from ideal condition. Okay. So, if you look at the definition of delta, delta is actually close to what value? Okay, let us look at the definition of this. Original definition of delta is omega H minus omega HO by omega HO. Then we got many other simplifications. So, compared to 1, say if you look at this definition of delta, omega H by omega HO minus omega HO by, so there is a difference of 2 terms. Both terms are close to 1. See, omega H by omega HO is close to 1. Is not 1, but close to 1. Omega HO by omega HO is 1. Okay. So, I am trying to take difference of 2 terms which are one term is 1, other term is close to 1. So, compared to 1, delta is small. So, that is the point. So, delta is very small compared to 1. So, if that is the case, then this impedance, that is reciprocal of the complex number YFH, can be written as that is 1 by GF plus JBF, can be written as R plus J. So, what is the simplification? Root LC is there, delta is very small into 2 delta, that is all. Okay. Now, let me take the imaginary part of this. See, the real part of the right hand side is resistance. Okay. Let me take the imaginary part. So, equate the imaginary parts. So, if I am equating the imaginary parts, so I am taking this equation 1 by GF plus JBF is equal to R plus J under root L by C into 2 delta. So, what is the imaginary part of the left hand side? 1 by GF plus JBF, GF and BF are real, conductance and susceptance. So, what is the imaginary part of the left hand side? Yeah, minus BF divided by GF square plus PF square. So, this is equal to the imaginary part on the right hand side is under root L by C 2 delta. Okay. So, I will write this in a slightly different form. GF square plus BF square okay, I will shift all the terms to one side. So, this becomes plus root C by L into 1 by 2 delta PF equal to 0. Is this okay? Now, I will do a few more manipulations. I will write this as GF squared plus BF square plus root C by L 1 by 2 delta BF plus, so I will add a term on both sides. So, the term is under root C by L into 1 by 4 delta whole square. So, this is added on both sides. So, what is the purpose? Yeah, I am actually completing the square. So, GF square plus, so on the left hand side what I get is GF square plus BF plus under root C by L into 1 by 4 delta whole square. So, this is equal to under root C by L 1 by 4 delta whole square. Suppose I take the graph on the abscissa, I have GF, on the ordinate I have BF. That is a complex plane with the real part equal to conductance and the imaginary part equal to susceptance. Now, the question is, if I take the equation that I just got in terms of GF BF, what is the curve? Circle, it is a circle.